Good evening, everyone. So today we are on our seventh day of the webinar series, and this day is very enchanting because we have two young speakers. Dr. Arghya Mukherjee, presently with IISER Kolkata, will be delivering the first invited talk from 6 to 7, and thereafter we'll have a students presentation session, after which we'll have another of our guest speakers, Dr. Amar Prasad Misra from Visvabharati Shantiniketan, who will be delivering the second invited talk today. And before we start, let me inform that today the local weather is a bit cloudy, and it is forecasted that there might be some huge downpour, so we might face some network issues. So let's pray that everything goes smooth. So the title of the first talk by Dr. Arghya Mukherjee from the Center of Excellence in Space Science, IISER Kolkata. The title of his talk is Breaking of Nonlinear Waves in Plasmas, the Kinetic and Magnetohydrodynamic Simulation Approach. So I would like to give a brief introduction about Dr. Arghya Mukherjee. Dr. Arghya Mukherjee has been my brother-like individual whom I love very much. He did his PhD from the Institute of Plasma Research in Ahmedabad, and the title of his talk is, Arghya, could you just title of his thesis? Arghya?
My title of thesis,
Yes.
Study of the breaking of relativistically intense waves in a homogeneous plasma.
Okay, and who was your supervisor?
Professor Sudip Sengupta, who belongs to the Basic Theory and Simulation Division of Institute for Plasma Research, Gandhinagar, Gujarat.
Okay, he is right now a faculty in IPL.
Yeah, he's in IPL itself.
Okay, so thank you once again. So, dear audience and students, my dear students, please gear up your notebooks because Arghya is going to present something very interesting and very helpful to the young participants like you.
Sure.
Thank you.
Okay, Swarniv, thanks for your nice words, and very nice to see you after a very long time. So, at the outset, I first expect that everyone is fine and doing well in this situation. Of course, we are going through very bad situation, and in this pandemic situation, the initiation of such webinars are very appreciated, and I am very delightful and very happy that Swarniv has invited me to give the talk here. So today I'll be talking about some my works, and which belongs to mainly the simulation study, and I will try to make the talk as simple as much I can. And if you guys have any questions, you can, as the organizer said, can post on the YouTube link, or later you can mail me whatever you want. I would love to answer to clear your doubts. Okay. So my today's topic is breaking of nonlinear waves in plasmas, kinetic and MHD simulation approach. So mainly I will show here the two type of breaking of nonlinear waves in plasma. One is using kinetic simulation and one is using magnetohydrodynamic simulations, so that the students who are new to the field can actually gain some idea that what the simulations are and what new things can be found by utilizing these simulation techniques. So mainly, first I will talk about the breaking of a high frequency wave in an unmagnetized plasma, which will be which has been studied using the particle in cell simulation code, is 1D PIC code, and the wave is high frequency and the plasma is unmagnetized. The topic is nonlinear propagation of electrostatic waves in relativistic electron and plasma. And number 2 is breaking of low frequency waves in a magnetized plasma, which is using magnetohydrodynamic code, is a Pluto code. And the second code is available online. You can free to download and study the way how it can be done in a HPC machine. And the second title of the second talk is nonlinear propagation of alpha waves in an inhomogeneous viscous plasma. So at first I will consider unmagnetized plasma, and the high frequency wave will be studied using a PIC code, which is kinetic in nature. And on the second problem, we have taken a magnetized plasma, where a low frequency, the breaking of low frequency waves will be studied using a MHD simulation code. So at first, let me introduce what is wave breaking. So when we have some wave, there must be some amplitude limitation associated with the wave. We know that when there is a wave, there must be a crest and trough. So one point occurs when the amplitude reaches a certain limit, that the crest of the wave overturns, as shown in the figure, that the crest of the wave just overturns and there is some singularity. And so therefore wave breaking also occurs in plasma, as a plasma can support an assortment of normal modes, which we call the waves. And when the amplitude reaches the critical limit, the wave breaking limit, the wave breaks within a period. But sometimes one situation also occurs when the wave doesn't break within a period, but it breaks gradually with time. So this process is called phase mixing. So phase mixing occurs only for one condition, that so one the necessary and sufficient condition is the characteristic frequency of the oscillation or wave, basically the mode which is propagating through the plasma, the characteristic frequency of the mode must be a space dependence. So basically that the modes supported by the electrons and ions of the plasma, so the frequency of their motion, of their oscillation, should be space dependent. So if the system in extend from x equal to 0 to x equal to some L, so at each point the electrons and ions are oscillating with different frequency, then only wave can break. So there is an example that first I have some equispaced electrons and ions or whatever particles. So when they move, so then the first they move, crest and trough occurs, and here the frequency is same for all the particles. But when the frequency is different, so we can see that the fourth number of particles, the fourth particle just overturns, means they cross each other. So this cross is not allowed for wave-like a motion to maintain a coherent type of structure. Therefore, we cannot allow this type of structure, and this is the wave breaking is. So therefore, this is called phase mixing. The particles which govern the dynamics of the waves gradually go out of phase and they destroy the oscillation. So of course, one pertinent question of course come that why we study wave breaking, means what new thing we will get to after studying the wave breaking physics in plasmas. So most of the thing that is the particle acceleration, that in a particle acceleration device, I mean the linear device, which is normally called a LINAC. So in LINAC device, of course, particles can be accelerated to a high degree of amplification, but one cannot extend the amplitude of the electric field up to a certain limit because of the thermodynamic emission and other physics. So it breaks down. So therefore, and number 2 is that in order to get a very high energetic particle in a linear device, one has to make a very long device. So therefore, long device means more money. So therefore, from the very beginning, physicists have thought about that if there any process to make it a more prominent way or more good way to get the more acceleration. So one thing is the plasma acceleration process. So what happens that in a plasma, as shown in the figure, that first a laser pulse or electron beam, electron beam or laser pulse is passed through the plasma, and this pulse actually creates a wave on the behind of the pulse. So this physics is quite analogous to the motion of a high-speed motor on an ocean. So when we have seen that when in an ocean a high-speed motorboat moves on the surface of the ocean, so there a wave, the wave generated on the behind of the motorboat. The similar phenomena also occurs in the plasma. Here the laser pulse does the job of motorboat, and the ocean is nothing but the plasma. So therefore, and what happens is that if a rider, if a rider rides on the wave, they can actually accelerate through the wave. And the rider is also an outside electrons. So on the outside electrons, if someone adds some electrons, so these electrons get trapped because the energy of the excited electrons, these electrons can be uh, equal to the phase velocity of the wave. So these electrons can directly see the electric field, and one can get a very high energetic of electric field within a very small device, in a tabletop device. And in this laser fusion, so basically the electrons which are actually trapped in the wave or the wake, they can actually generated via wave breaking. So for this, one doesn't need to give a outside beam from the outside, which also make a good promising process, the self injection process. So means first the laser pulse creates a wave, this wave breaks, and from breaking the energetic particles generated, these generated particles rides on the wave on the later on, and they accelerate it. Okay, so this is called self injection mechanism. And number two is the laser fusion. In a laser fusion, what happens is that there is a deuterium tritium pellet on which the high energetic electrons are laser are impulsed, so which can generate to get the more energy to the hydrogen tritium pellet to get the more energy, and this is accompanied by the high energetic particles which is already generated by wave breaking thing. And one another natural thing is that we know this is the sun, very familiar star of our system, and the aura that is outside the sun is the corona. And surprisingly, the temperature of the corona, means outside of the sun, is much higher than the photosphere and other things. So from where this energy comes? So this is the temperature. You can see that from photosphere to chromosphere, the corona, there is a high jump. So from where the temperature rises? Because is that because of the magnetic field, there are some alpha wave are generated. This alpha wave breaks, and their alpha wave energy actually gets transferred to the random particle energy, and random particle energy is nothing but the temperature. So this is also a manifestation of wave breaking physics in the coronal heating problem. So first, let me get into the first job work, the nonlinear propagation of electrostatic waves in relativistic electron plasma. So it is a one-dimensional unmagnetized plasma comprising of electrons and ions, and they are moving relativistically motion, means they are moving so fast so that their motion is relativistic. So relativistic means that when we generate a wave, the work done by the electron and ion, whatever, within a wavelength of the wave is comparable to the response energy of the electrons. So E lambda means E is the electric field, and small e charge time electric field is the force into displacement over a wavelength is lambda. So electron charge into electric field into wavelength, should be comparable to the mc square, means the mass into into light speed square, means the rest mass energy. This is the definition of relativistic waves. And when this condition satisfies, only then the electron and ion actually move relativistically. So let me give you a very brief introduction of particle in cell simulation. So it is the step is very easy. We know that in phase space, there are six variables. One are three momentums and three positions. And similarly for here also, at t equal to 0, at initial time, the particles with specified position and specified velocity are introduced in a system. So specified positions are given from the density distribution, and specified velocity is drawn from the specified current distribution. So according to the problem of density and current, we can generate a position and velocity of the particles. Okay, so now once we get the position and velocity of the particles, we can eventually solve the equation of motion of the particles from electric and magnetic field. Okay, so from initial electric and magnetic field we can do it, and from next is the from this equation one get the new position and velocity. From new position and velocity, one needs to interpolate the position to the different grid space where the electric and magnetic field is found. So once new electric and magnetic field is found, so this again interpolated to the new particle position, and this is actually moves on. So first, new x and v are given. So from x and v, from electrical magnetic field are calculated. From electric and magnetic field calculated, then they are again pushed back to the particle position. So then equation of motion is solved. So from equation of motion is solved, the new position, new velocity are obtained. From new position and new velocity, again new electric and new magnetic fields are obtained. So this is the way the particle in cell simulation works. So the flow diagram is quite easy, but it is not that easy to write this code. If anyone is interested, I would suggest to download from Berkeley website. There is a free code is available there, and other is the KEMPO 1D run, which is available in MATLAB. And presently, I am also writing a PIC code in Python actually. So hopefully, I will make it available for users. I don't know when, but whenever I will get time, probably I may need another 1 year. Anyway, so if I made it, I will make it online. Okay, so now the theoretical description is that a longitudinal relativistic traveling wave solution supported by the both electron and ion motion in an unmagnetized plasma can be derived from relativistic two fluid model. So first is electron momentum and electron continuity equation. Second is ion momentum and ion continuity equation. So electron motion and ion motion are coupled by the Poisson's equation. So one electric field which is coupled from electron and ion density. So once electron and ion density are found, this can be used to get the new electric field and new density of the electron and ion. So after a few algebra, we can find out that this is the equation of motion in the traveling frame, where the phi is given by 1 plus E phi by mc square. So E phi by mc square is a normalizing factor, and phi plus is 1 plus mu into 1 minus phi, where mu is the electron to ion mass ratio, and chi is the wave frame, so kp into x minus v phase t, and beta is the phase velocity with normalized to velocity of light, and gamma is the Lorentz factor, and kp is the Bode number, omega p by v phi. Well, so now few previous theoretical works. From the solution of the previous equation, one can find the fluid variables like this. This is the electric field and the velocity and the density, and the maximum electric field amplitude, wave breaking field, is given by this factor. So square root of gamma into 1 plus 1 minus xi1 half, xi2 half by mu, where xi1 and xi2 is given by this factor. So xi1 and xi2 is a function of mu, means, and gamma. So they both, electric field is basically a function of the electron to ion mass ratio, and their Lorentz factor, means Lorentz factor. So these are the theoretical solutions for two different profiles. One is for mu equal to 1 and one is for mu equal to 0.0 e 0.01. And so these profiles needs to be loaded in a PIC code. So that is what we exactly did. So this density and this velocity and this density and this velocity profile are taken, and we have found out a nice uh, polynomial fit, and this polynomial fit has been loaded in the PIC, and from this PIC evolution of the code, evolution of the wave in the system can be found. Well, and this is for another case for higher electric field. So basically this is the system. So at initially the blue line is the equilibrium position of the electron and ions. So next the ions are displaced from to the left position of the equilibrium position, and ions are displaced to the right from the equilibrium position, and then we get the electric field. So if I picturize this phenomena, we'll get this thing. First, electrons and ions are in the same position, and there is no electric field. As I told you that the first electrons are displaced to the left position, which is given by the this density distribution, and ions are displaced to the right position. So this is gives a ion density. So here electron density is high, therefore the electron position is quite congested here, and here the ion density is high, therefore the ion positions are quite congested here, but here the inter-ion distance is quite large because of the low density, and similar for electron. And this type of distribution, one get the electric field of like this. This is the electric field we get. So if we load a density and velocity distribution like this, we will get an electric field of this form. So therefore, we have actually loaded this profile, and we have got these results. For this, the result has shown stroboscopic plot for 2 plasma period, and we have seen that there is some good match with the theory and simulation results. So here the red lines are the simulation, and the blue dot lines are the theoretical results. And this is the 3D picture of the potential, electric field, and electron density that both are flowing, and the theoretical agreement is excellent. And on a grid point, the electric field density and ion density are shown for two different profiles, and we found out that this is the dispersion relation of frequency of the wave is given by this parameter. This is the expression where r equal to a minus 1 by a plus 1, and a equal to is nothing but the Lorentz factor actually. So for which is corresponds to the energy of the electron and ion, and for non-relativistic electron positron mode, the above expression for of frequency leads to square root of omega pe. So now for simple case, why there is no breaking? Because the energy is space independent. Because of the energy space independent, we can observe that up to a certain period the wave is propagating, as shown in this figure here. So omega pt up to 30, the wave is propagating without any breaking, because there is no space dependent frequencies here, because all the frequency is same. So in order to make a space dependent frequency, we have to make a space dependent, means we have to part of the system. So again we have part of the system. Okay, so before the partition we have verified this dispersion relation with mu and k for two different values well. And next we have added an external perturbation, and we have found out that there is some now different structure is getting, and the wave is actually breaks after a certain time. So here is the electron density is also some modulated, and the electric field also gets modulated, and electron density is also makes a peak because of the gradient in electric field, and the ion density also shows a peak. And for this parameter also, different parameter also, And but for different view, the time is different actually. Also, we have got the modulation of the electric field and the high peak in electron and ion density, but the time is actually different. So we have defined the time. We have also calculated the time from this from theoretical analysis. We have found out that this phase mixing time is given by beta, which is the phase velocity, divided by delta E into V max square plus mu, which is the electron to ion ratio, by delta I V max Vi max. So delta E and delta I is the perturbation to the electron and ion velocity, and for different delta value, the phase mixing time with delta has been calculated, and we have found out that the peak simulation follows our theoretical prediction. And for a fixed delta value, we have changed the value of the mu, and we have also found out that the for a small value of mu, the phase mixing time strictly follows the peak simulation results. Also, we admit that uh, there are some violation of our theory for higher mu value, but it is quite anticipated because the theoretical expression that we have derived from the theory actually is taken that mu is very very less than 1. It is given that mu is very very less than 1. So the mu is very close to 1. Actually, there is some deviation. It is actually anticipated that there should be some deviation from the theoretical. But for a smaller mu value, means for a hydrogen plasma and other things, our theory works very well. So the conclusion for the first work is the space-time evolution and breaking of relativistically intense waves, uh, supported by the both electrons and ion motion, have been studied analytically and by performing particle in cell simulation method. Traveling wave have been exciting particle in cell code. The dispersion relation have been derived and verified by simulations, and it has been found that these modes break via the process of phase mixing far below their conventional wave breaking limit when part of longitudinally. It also shown that the phase mixing time scales has this formula, and further the analytically obtained phase mixing time scale has been verified via peak simulation for a wide range of input parameters. So next we move to our second problem, which is the not this is the current problem I am working on using the Pluto code nonlinear propagation of alpha waves in an inhomogeneous viscous plasma. So this is the MHD equations we all know, and this is the alpha wave generated in the Pluto code. So this is so there is an this is x-axis and this is y-axis. The magnetic field is given in the x-axis, and the perturbation is given in the by direction, and therefore we can see that the wave is propagating along the x direction. The magnetic field is propagating along the x direction, which is a resemblance of the alpha wave. And to give a more sophisticated picture, let me show the dancing of the magnetic field lines. So consider that the magnetic field is applied in the x direction, and this is the total magnetic field, how it looks like. So you can see that the magnetic fields are oscillating along the y direction, but the wave is propagating along the x direction. So this is actually alpha wave. So in order to get a phase mixing, we have to make a inhomogeneity along the y direction. So then what will happen? So different field lines will oscillate with different frequency, and a phase mixing time of phenomena will be seen. So next we will move to that. So before we move, there something else to be shown. Okay. Okay, so first let me show for our MHD simulation results of alpha wave for a homogeneous viscous plasma. This is at t equal to 0, and this is as time progresses, we see that the amplitude of the alpha wave decreases. And why it is decreasing? Also it is propagating, but that is decreasing because the amplitude decreases because of the viscous effect. This is called the damping of the alpha wave. This Landau damping kind of stuff. And this damping, we have also measured the damping coefficient and the damping with time, which also follows the theoretical prediction, but we just made it. I just got the result yesterday night or tomorrow morning, so I couldn't time to plot show all the plots. I apologize for that I couldn't show it. And but this is the actually the phenomena. And for a homogeneous case, the electron density is shown, sorry, the total density is shown, because in MHD there is electron density. One, we have the only single fluid density. I'm sorry. So therefore, we have seen that some modulation are also observed in the density because of the inhomogeneity parameter. So there is the inhomogeneity is introduced along the y direction. So here the is 1 and it is 5. Okay, and this is the y component of the magnetic field. You can see that here in this direction, because the magnetic density is low, therefore the here the field, the velocity of the alpine wave is quite higher than this position, therefore it moves fast, and therefore this structure also got, and this is it is called phase mixing. But here please note that the initial amplitude was 0.2, here also is also 0.2. The amplitude doesn't change because there is an ideal case, because there is no viscous and ohmic term is introduced. I will show one result when this term is introduced and what will happen. And another interesting is that the X component of magnetic field show such kind of phenomena. It occur because that the X component also excited some other type of modes, probably some magnetosonic of structure, and this also generated in those places where there is an inhomogeneity in the density is present. See, in the other places this structure is not generated. It also generated in the gets generated in the region where there is a sharp change in the density. Okay, this is for viscous case, and viscous case we see that as time goes on, the amplitude already decreases, which is also anticipated from the damping model. And for the for BX component also, X component also, we also got the structure is also generated, but the amplitude is also decreasing with time rapidly, which is actually possible for the damping case. So okay, up to this, and presently as I am working on this, there are other things to come very soon that will be shown in, in our some next talk whenever it will be possible. And today I will completing by here, and if anyone has some questions, as I have some time probably, so I would like to welcome few questions if possible for someone.
Well, so far there are two questions. One from Aditi Bose. She is asking that, sir, can you elaborate more on the definition of a relativistic plasma?
Okay, so relativistic plasma, and basically relativistic plasma is that when you have some solid target, suppose you have a very solid target and you have a very high power laser, so you have impinged the solid target with a high power laser. So what will happen that, so here we will have a very high temperature plasma will generate. Okay, so there the electron distribution will not be a Maxwellian, because Maxwellian distribution is not relativistically correct. Always remember one thing. So we know that Maxwellian plasma have some left limit and some right limit, and more temperature, and we have got more flat distribution. So always remember that when the temperature is V thermal, the distribution also extends from minus √3 times V thermal to plus √3 times V thermal. So for some cases, one temperature will arise that your velocity limit will extend the velocity of light, but it will not Lorentz invariant. So therefore, for such cases, you will have a different relativistic Maxwellian distribution. It's called Jüttner distribution. So when the plasma, there is some Jüttner distribution, you can call it relativistic plasma. But another thing is that relativistic plasma and relativistic wave, both are different. So relativistic plasma means the electron distribution, means charge particle distribution is quite high energetic, means you can call it as Jupiter. Okay, for if you need more information, you can mail me or contact me.
Well,
And
Orko,
and
just
for wave,
the name of the distribution. So someone is asking to clearly say.
Jutner, G-U-T-T-N-E-R,
Jupiter.
J-U-T-T-N-E-R, Jutner,
Thank you.
J-U, and number two, relativistic waves means when the work done by the electric field, within the wavelength is equal to the rest mass energy of the electrons or ions. This is called relativistic wave. So there are two different points. Okay, so please remember, relativistic plasma doesn't mean relativistic wave. Okay, Swarniv, is it clear or hello?
So the question raised by Aditi was elaborately clarified. Thank you, Orko. And the next question is from Nitika Ghosh. She is
Okay.
asking that, sir, how to get the course, and is there any course for learning this simulation? Basically, she is a final year graduation student, just completed her graduation or would be appearing for the exam. So she has got this question. Is there any course to learn the simulations?
Of course, there are several codes you can also download. And first of all, you need to define what you are trying to do. If you are studying MHD, there are enormous number of free codes are available. One is Pencil, number two is Pluto. Pluto I have downloaded. You can also download and study the manual and run it on your own laptop. There is the only way you can study or learn. Nobody is going to teach you. So this is the only way you can actually run your own code. And for PIC and for kinetic codes are also available online. You can search for Berkeley code, and number two is Kempo, Kempo, Kempo code in MATLAB. This is a PIC code in MATLAB. So that is quite easy. You can also download it. And if you are going for PIC for higher dimension, then also you have epoch and other type of codes. So several codes are available in the market. So just you can Google it and you can find.
Well, Argo, that was a beautiful talk and very much resourceful as for the new students or students who are interested in simulations, because Argo's whole PhD work and all his presentations so far that I have learned is all dedicated on simulations.
Yeah.
So I have known him from the first year of his, first few months of his PhD.
Yeah.
And till this day, and he has bloomed like a big flower, and I congratulate you on my behalf and many loves, and thank you. And I think if anybody have any more questions, please raise it now, because
yeah, sure.
well, it's on applause. Thanks and congratulations.
Okay,
The
thank
live
you,
chat box.
Thank you, Swarniv. And I first and finally just say all the students that just learn, and whatever you want to do, just download and Google it. Google is the master, and you can find everything you can want. And just
Well,
keep
Orgwar
your
said
patience.
the
And
truth, and because you can just look for the open source, and if you have
yeah,
any interest in learning anything, the only thing is that, because when we were quite young, the internet was not that much available, but right now your generation have got internet like anything at your palm top, so you just explore it. And apart from doing any apps or just playing this games, and I would say these video apps that they find, I'm not naming anything, so it's better to learn something that will benefit you. So
yeah. And
thank you all.
and another thing is there is also a app for MATLAB in mobile.
Yes,
And if
because
you are
all
traveling,
the workshop that we have done in the last 2 months, most of the time the students complain that it is not that much, we don't have that much space, or it's not possible to download, or it's a premium, so they just got it for the mobile app, somebody, and they did it. And this was quite a great resourceful
of course.
thing.
Of
Yes,
course, of course.
yes.
Okay,
So thank you, Argo.
okay,
Thank you for coming here. And it was
okay. Thanks for
really
inviting.
a wonderful talk. I myself learned a lot of things. Yes, yes. It just felt like so much in a very crispy way you have said, just without using much of jargons, much of technical terms. It's beautiful. Awesome.
Yeah. Okay.
Thank
Okay. Okay. Thank you.
you. Okay. So, dear audience and students, we have our next uh, three speakers. Basically, it's a students presentation slot, and we have two presentations. The first presentation will be by three authors simultaneously: Ananya Ghosh, Devjit Maiti, and Shumon De. Now, a brief introduction about the joint presentation. I would say that Shumon De is from Visvabharati Shantiniketan, and Devjit Maiti is also from Visvabharati Shantiniketan, and Ananya Ghosh is doing her masters from Bethune College and the University of Calcutta. And the study of their talk is today's study of rock waves and rock waves in nonlinear excitations of plasmas in ion acoustic mode with kappa distributed electrons. So let's welcome the speakers, please.
Yes, sir. Yeah, it is visible.
Yes, it is visible. Just carry on.
Yeah, am I audible?
Yes, you are audible.
So, good evening, everyone. I am Sumonde from. I am pursuing masters in Visvabharati University, and I want to discuss today the study of rock waves in nonlinear excitations of plasmas in basically in the high energetic kappa distributed electrons. Uh, I worked this under the guidance of Dr. Swarniv Chandra, and I worked at summer workshop on plasma physics 2020. And let's begin. Uh,
Well,
First of all,
Shumon, you just raise your voice or you set up your mouthpiece a
okay,
bit.
okay, sir. Is it okay? No.
Yes, it is absolutely fine.
Yeah. Now I'm going to first of all I'm going to thank my group mates Devjit Maiti and Ananya Ghosh for their uh, help and for their effort. Uh, so first of all, let's take a look about the table of contents. So first we uh, talking about the what is plasma, and next the mathematical description of plasma and kind of oscillations in the plasmas and the waves, and our most our the study of rock waves is our main the main thing of our work is study of the rock waves and the stability of the rock waves, then the basic equations formulations, and then the linear characteristics as well as the non-linearity of the rock waves, uh, and our future plan also. So before start, the things we need to know that this plasma is kind different with the blood plasma. In physics, the plasma means the ionized gas which contains the electrons as well as the ions. This is totally different from our the blood plasma. Now, a plasma is a quasi-neutral gas of charged neutral particles which exhibits a collective behavior. Now, what is mean by the quasi-neutral? Now, quasi-neutral means basically uh, the equal equal density of electrons and ions. Approximately equal densities of electrons and ion means the quasi-neutrality. And the collective behavior means basically uh, the way the overall behavior of the plasma is a sum of the individual particles behavior. This basically means the collective behavior. And uh, the plasma is the fourth state of matter. We basically see in plasma in the high temperature. Uh, the example of the plasmas we seen often the lightning and the auroras in the northern side, and also the solar wind. And also we are familiar, we very much familiar with the fluorescent light, that also a plasma. So next, what is the mathematical descriptions of plasma? Now, in mathematically, plasma can be described by two kind of models: fluid model and kinetic model. Mm, and we basically use the fluid model because just to reduce the complexities of the kinetic description. Uh, the fluid model includes the macroscopic quantities like the velocity, the mean velocity, and the energy, the momentum. Uh, this is quite familiar with kind of working with kind of things. And now, as we uh, as we uh, consider the fluid model of plasma, so there can be turbulence like fluids. So the plasma turbulence can be occur in the can be occur. So let's take a simple example how plasma oscillations or the turbulence can be occur. I have taken three sheets of charges, and the middle sheet is displaced uh, d. For the displacement, there will be generated some force, and for that force, the oscillation can be generated. And for that oscillation, a wave can be generated. This wave basically called the Langmuir plasma wave, or the Langmuir plasma oscillation frequency can be written as like this. This frequency is dependent on the density of the electron, the charge of the electrons, and the mass of the electrons. Now, here is a simulation uh, taken from Wikipedia, is shown here. The red dots are the ions and blue dots are the electrons. Here you can notice that the uh, electrons are very much mobile than the ions. So basically, we have taken the hot electrons are very much mobile than the ions. And coming to the next, our main perspective of the study is the what is the rho waves. Now we basically studied the rho waves and the stabilities. Now rho waves kind of thing that is a very much a very high height. You know, the kind of the highest third of the observed wave height. This is kind of rho wave. This is simulation of rho wave. This the high amplitude wave can be generated in the nonlinear phenomena. This wave is called rho wave. This can be seen in the systems including the liquids, water, and as well as the plasmas. So we basically studied the rho wave in the ion acoustic mode. But what is the ion acoustic waves or the ion acoustic mode? So in plasma physics, ion acoustic wave are kind of a wave that is pretty much like the acoustic wave traveling in neutral gas like helium, argon. So as this is acoustic wave, uh, we can imagine as a longitudinal oscillation like compression and the depression and that kind of wave, as I previously I shown the as a Langmuir waves. So this is the acoustic wave, kind of longitudinal oscillation. And what is the plan of our work is uh, the to find the possibilities of generation of rock waves in the propagation under the Kappa distribution. Uh, Kappa distribution basically means the high energetic case. Now, we as well as we studied about the linear dispersive characteristics. That means the omega versus k, and and we imposed the KDB equations and the modified KDB equations so far. Uh, in this process, we have used the reductive perturbation method. The reductive perturbation method are uh, the means that we use the perturbation in our physical quantities like velocity, uh, gen, uh, velocity, density, and the electric potentials. Now, how kappa distribution can be described? Now, kappa distribution functions will be described to be defined as like this, where the omega kj is the most probable speed of the particle or the thermal speed, the speed due to the temperature. Tj is the characteristic temperature and v is the velocity of the particle. Now, at kappa tends to infinity, the distribution function drops to the Maxwellian distribution, as we are familiar with that very much. That is density equals exponential of phi. Phi means the electrostatic potential. At kappa tends to 3 over 2, the equilibrium goes to the anti-equilibrium. Now, we have considered here the hot electrons, and basically the high energetic case in hot electrons are very mobile than the cold electrons, and so the momentum equation can be dominated, the basic equations can be dominated only for the ions. So electrons, the equation of electrons can be omitted. Now comes to the basic equations. These first three equations are the unnormalized equations. Uh, the first one is the continuity equation. The second one is the momentum equation. Here we have taken the collisionless, and um, we have omitted the magnetic terms. We can add these terms, but that will be too much complicated. That we have neglected that, we have omitted these parts. And the third one is the Poisson equation. And by normalizing these three equations, we have got this. Normalization means basically to dimensionless those equations. Next, we studied the linear characteristics. As I have said before, that the perturbation expansion for electrons, and we have used the perturbation expansion by putting this and evaluating the time by exponential of this term, and we restricted ourselves for the first order perturbation. We have got these uh, relations, uh, and putting these two relations in the Poisson equation, we can got uh, we can get this uh, equation with respect to omega and k, and we plotted the graph, and we kind of like dispersive nature. But notice that if kappa value exceeds, if kappa value is 3 over 2, then this relation can violate it. So there will be some limit, there will be some critical value of kappa above which the wave should be unstable. So now before start to the before go, start to the non-linearity, we will just go to a brief introduction of family of KDB equations. Now KDB equations are the most basic KDB equations is this, where the partial differential equation can be written. There should be second order partial differential equation, but this will be called as the modified one. So what is the significance of this KDB equation? Now the second term in KDB equation tells us the non-linearity. It represented the non-linearity of the wave, as well as the third order term can be represented the dispersive effect. So the KDB equations is pretty much very it's very effective for studying the non-linearity. So we generally use the KDB type of partial differential equation. So at first we taken stretching variables. So the stretching variables are taken as this to To balance the orders of epsilon, we taking this stretching as like this. Now we have stretching taken the stretching like this and derived this KDB equation, where n is the nonlinear term, where n is dependent on the mu, the mass ratio, and the temperature ratio, and V0 is the normalized velocity of the wave, and beta k is dependent on the kappa. Beta kappa is dependent on kappa, and U0 is the velocity, and D is the dispersive term, is responsible for the dispersive nature. It's dependent on these quantities. Now there is so many stationary solutions, and tan hyperbolic and sec hyperbolic. We basically studied the sec hyperbolic solutions. So we have taken the sec hyperbolic solutions where psi m is the amplitude, and we have plotted this type of we have get this type of graphs uh, for the different value of V0 and different value of kappa, and we plotted in 3D. We get like this. Notice that at a certain value of kappa, the graph will be switched to upside to down. So there should be a critical value of kappa. So we are going to study this basically. So coming to the uh, soliton of the rock wave and derive the equation of the rock wave. Now to do this, I basically obtained the modified KDB as the previous technique, but taking stretching as the new stretching. We obtained the modified KDB as we done previous for KDB. We get a equation like this, and here also n1 and d1 is dependent on the variables like mu, the mass ratio, sigma, the temperature ratio, and v0 is the velocity of the wave, normalized velocity, and beta k kappa is the function which dependent on kappa. So from this modified KDB, we derive the nonlinear Schrodinger equation. Now the nonlinearity comes here, the third term, q psi square psi star is the nonlinear term. Q is responsible for the nonlinearity. Now where the P is like Q is like this. And approaching to a Peregrine soliton. Peregrine soliton means basically we have studied the only the first order solutions. I mean the peak will be 1. Here we will got the only one peaks. There should be other soliton, but we have studied only for the first order. Now this soliton leads to psi equals like this root over p by q, and we have plotted the 3D simulation for the different values of theta and rho. Kind of simulation. The height of the amplitude is varying very much for a different value of theta and rho. Now we're going to study the stability of this wave. Now we have plotted basically the PQ over K. When n1 tends to infinity, when this n1 term, nonlinear term tends to 0, then in this equation P tends to infinite, P tends to negative, and Q tends to negative. Q will be negative and P will be negative. Q will be positive, sorry, Q will be positive and P will be negative. Overall P and Q, the multiplication, PQ will be negative. If PQ will be negative, the wave, the equation drops to KDB equation. Now, if the equation drops to KDB, then the instability will vanish. The wave becomes stable. We have noticed that thing. So for this case, raw wave cannot be generated. So we have taken here, we basically do this modified version of KDB equation because of this, the instability, to describe the instability, to generate the raw wave. So there must be a value of there must be critical value of k for which this kind of situation may be occur. So we have basically plotted the pq over k from which I got from this nonlinear Schrodinger equation and the Peregrine soliton. So pq plotted against k, and we plotted this um, and we get a critical value above which the value of pq will be positive, and below that the pq will be negative. So at that point the uh, k is we call this a critical value. So above this the wave becomes stable, and below that point the wave becomes unstable. So above that value the raw wave can be generated. Below that value the raw wave cannot be generated, and that's our main perspective of our work. So basically the non-linearity comes from the q, this q term. So the non-linearity is comes from the q term. So this can be negative or this can be positive. So p and q should be between so p can be greater less than 0 and q should be greater than 0. This is the uh, for this we the raw wave can be generated within this value of p and q. So uh, we have we have get a critical value of kappa like this, which will be dependent on n1. So critical value of kappa 1 and the instability will depend on n1 and q as well as. So we have this get a critical value, and that's our the motive of our study. So come to the conclusion. In summary, uh, we have discussed the generation of raw wave. So the raw wave can be generated, as we've seen that raw wave can be generated for very short time, and the period of the time is very short, and raw wave can be generated only for modified KDB, not for the KDB equation, because the nonlinear term can be will be vanishes, and no there will be no stable raw wave. There will be no stable wave, uh, uh, and in nonlinear wave q factor, the q is the only responsible for the generation of raw wave. As well as we discuss about the generation of raw waves, and in the study is almost clear to understand the nonlinear excitation of ion acoustic mode. The ion acoustic raw wave can be seen in many laboratory plasma, as well as the stellar objects like Earth atmosphere and Saturn's magnetosphere, solar wind plasma, etc. And we have got the reference from these papers. Uh, and our future plan includes the implementation of magnetohydrodynamic phenomena. We don't include the magnetohydrodynamic phenomena. The magnetic terms and the collision terms is not included in this study. So future plan we will going to include these terms, and going to study those instabilities, and we're going to study the instabilities for the solar flares. Basically in the we going to study the solar flares instability, various type of instabilities, like the pair instabilities and Jeans instabilities and others. And we are going to study further for the low frequency magnetic waves in basically the solar region. So thank you for giving us your time, and thank you.
So thank you, Shumon, for your wonderful talk. So we have some the co-authors also are there live, and The video is totally paused. Wait, probably that was the video was not audible, maybe due to the other things. So could we just go to that video, or Shuman? Was there any video there? So any sound?
What's that?
So Devjit Maiti says that I can't hear sounds properly. Well, I could hear, so you were audible. Maybe some other things were your problem. So is there any questions from the chat box? Just wait, Shumon, Anonna and Devjit. We're just waiting for any questions to come up.
Okay.
So from the audience, is there anybody out there with a question? Well, I have a query. Could you just go back to your slide where you got the peregrine solution?
Okay, 1 minute. Here.
Yes. Yes. So, some people, it is a question not from my side, but from a general perspective that people might come up, that here rho and tau, theta, rho and theta, these are the transform coordinates, that is the space and the time part. So the space part can be negative, but for the time, so if anybody asks that what is the justification of the first order Peregrine solution's negative temporal part, so how would you suggest or like to shed light on this?
You mean the time is negative?
Yes, tau, theta is negative.
Okay. When the time is negative, basically we, as per my knowledge, it will be wave, kind of backward wave. I think the wave will go into backward direction. As per my knowledge, it will be kind of for negative t. The wave
Backward or the previous part of the wave. I think rho and theta are related to the first part, and which that means that they totally rho and theta, when they are combined together, they form the phase. So over time, if we are looking towards the negative side, that means we are looking at a previous thing. So some question is there from Yes Nobi. Yes Nobi, he is asking that what are the applications and advantages of studying log waves? Well, it's a good question.
I have.
Yes, Nobi. Well, yes, Nobi, could you just type from where you are in the chat box? Well, you clarify in his query, studying the log waves. What is the advantage?
Raw wave can be seen. I have said here, raw wave can be seen in stellar objects, in like the everywhere in plasma, in the high energetic plasmas. There will be seen the raw wave kind of instabilities. So it can be very almost clear for understanding for in the Saturn's magnetosphere, any astrophysical phenomena. Solar wind, we are basically working with this currently, the aurora and kind of very high energetic cases, we will find this kind of raw waves. Is there any questions? Hello?
Yes, so far no questions. So thank you. Thank you, Shuman, Devjit, and Anuna. So your presentation was quite beautiful. And now we have a student presentation from Egypt, Nora El Shafei. So Nora will present her talk, and after that we will have an invited talk by Dr. Amar Prasad Misra, and the title of Nora's talk this evening is.
Hello, sir.
Yes, you are audible. You are audible. So Nora's talk is raw waves in DF regions of Earth's ionosphere in the presence of superthermally distributed electrons and positrons. So before we start with Nora's presentation, I would like to inform that Nora is the student of Professor Salah Kamal El Lebni and Professor Well Farouk Al Tebni, and also Professor Nabila Ahmed El Bedwi. Well, they are all from Damietta University, and often we find their works in our literature, and Nora represents their group. And we have another two participants from basically all student participants and viewers. They are mm, they are Mahmoud Bakri and Amun Gouda. Amun Gouda and Nora. Could you just start your presentation? We are eagerly waiting for a international presentation from the students
Yes,
part.
yes.
Thank you. You just introduce in a few words about your university, so that will be good for everyone to learn about.
Screen share here.
Yes, you can share your screen is visible, and we can watch it.
Yes. Welcome, sir. Hello, everybody. My my name is Noura Ahmed Al-Shafai. I am from Egypt. Today, I will present our work that have a title Rock Waves in a weakly relativistic warm plasma with non-extensively distributed electrons. Now, supervisors, Prof. Salah Kamel Al-Labani, Professor of Theoretical Plasma Physics, Physics Department, Faculty of Science, Damietta University. Prof. Wael Farouk Al-Taibani, Professor of Theoretical Plasma Physics, Department of Physics, Faculty of Science, Damietta University. And finally, Prof. Nabila Ahmed Al-Bedwihi, Prof. of Applied Mathematics, Maths Department, Faculty of Science in Damietta University. Outline of our work: introduction, plasma in nature and technology, plasma theories, mathematical techniques and evaluation equation in theoretical plasma model, aim of the work, Kaplan equation and the derivation of nonlinear Schrodinger equation. This derivation equation for finite wave number and derivation of nonlinear Schrodinger equation from KDB equation. This equation for small wave number approximation, log wave solution, results and discussion. Firstly, what is the plasma? The plasma is a fourth state of matter. If we consider the state of the solid state of the solid of matter, if we increase the energy or the heat of the system gains energy and convert it from solid state to liquid state. And then if we increase the temperature, the liquid goes to gas. Finally, if we increase the temperature to very high temperature, the gas goes to a plasma of ionized gas. Another definition of plasma. A plasma is a quasi-neutral gas of a charged and neutral particle, which exhibit a collective behavior. Why we say the plasma is a quasi-neutral gas, not neutral gases? That because that not all particles have ionized, and not all particles have the same degree of ionization. If we consider we have oxygen may be lost electron or two electron, and if we have argon or fluor, we may be lose one or two electrons. Consequently, this gives us impression that the plasma is not a single gas, but contains more than one of gas. Plasma criteria. What is the plasma criteria? If we consider that L is the dimension of the system, dimension of the system must be very larger than the pi length, and number of particles in density ND in the pi sphere must be very high than one. Plasma frequency the product of plasma frequency and the mean time between collision must be greater than 1. Ion acoustic wave. What is the ion acoustic wave? Ion acoustic wave is a type of longitudinal oscillation of ions and electrons in plasma, much like acoustic waves traveling in neutral gases. Rogue wave, also known as killer wave, giant wave, or freak wave, is a rare, singular, short-lived, and higher energy event with a very high amplitude. This is the shape of rogue wave. Plasma in nature and technology. Plasma there exists in nature, such as sun and stars and aurora, lighting, sorry, lighting nuclear cloud, and the technology may be in lighting, plasma display, in plasma TV, laser production, melting, cutting, spray coating inside tokamak. We deal with plasma deal with surface treatment. How? Eliminate surface contaminants. That is before figure, and that's after eliminating. Plasma chemical removal of corrosion before treatment and after treatment. The first, wound healing. The plasma in medicine, plasma can be used to treat wounds, such as after 5 days. This figure, this picture, and after treatment after 15 days. In this dysentery, the plasma is there. Sorry,
Nora, just your
there is a
microphone, could you
problem.
just take it? Nora, your microphone, could you just take it close?
And in dentistry, the plasma can be, yes, close.
Yes, your microphone, can you take it a bit close? Because voice is breaking.
What is the problem?
No, now it's okay, okay, right now. Fine, okay.
Plasma series. Magnetohydrodynamic model study the plasma as a single fluid. And the fluid model deal with H species as a fluid. Kinetic theory, it considers that the velocity distribution function for H species. This velocity distribution function is a function of 7 variables, 3 in space, x and y and z, and 3 in velocity, vx, vy, and vz, and the time. There exists simple model uh, also studies the plasma called single particle model. This single particle model deal with a plasma as a single particle. Mathematical techniques and evaluation equation in theoretical plasma. Models equation. Fluid theory. Fluid theory can be contains the 3 main equation: that continuity equation, equation of motion, or so-called momentum equation, and Poisson equation. We deal with linear analysis such as dispersion relation, and nonlinear analysis such we deal with reductive perturbation technique, such nonlinear evaluation equation, such KDB equation, ZK equation, and ZK Berger equation. And derivative expansion method deal with nonlinear evaluation equations such nonlinear Schrodinger equation, arbitrarily or large amplitude, energy like equation, such Sagdiv potential. Nonlinear Schrodinger equation. Plasma, this deal with plasma instability and stability. Can be can be studied by multiple scales method, derivative expansion method, Kirilyov, Grigorov, Mitroblowski, or KBM method. We deal with multiple scales method as this is a more general than other methods. Labani et al. Studied the modulation instability of a weakly relativistic ion acoustic waves in a warm plasma with non-thermal electrons in 2003. In 2020, Labani et al. Studied the modulation of nonlinear acoustic wave in a weakly relativistic warm plasma with super thermally distributed electron. Aim of the work. The previous paper it studies that the ion acoustic modulated ion acoustic wave in a weakly relativistic with different distribution, but doesn't deal with rogue wave and doesn't deal with super thermally distributed electron. So in this work, we deal with this rogue wave and the super thermally distributed electron. We study the stability and the instability domains and study the effect of physical parameter of the system in this stability and instability regions and on the rogue wave amplitude and the solution. Govern equation and the derivation of nonlinear Schrodinger equation. We have three main equation. Continuity equation. This is equation of conservation of number density and equation of motion, conservation of momentum. This equation have a relativistic factor and thermal temperature ratio, ion to electron temperature, and adiabatic pressure and electric field. Finally, we have Poisson equation that have electron density and ion density, nabla square phi, where electron density have a form in non-extensively distributed electron in this general form where alpha 1 and alpha 2, alpha 3 take the form. Employing the multiple scales techniques, this stretching we deal with. We using this stretching and the dependent variable in the main equations, and we obtain on and we use the relativistic factor in this form. If the particle velocity is much less than the velocity of light, ions will exhibit the non-relativistic behavior. But when the particle velocity approaches that of light, this effect must be the relativistic effect must be considered. For weakly relativistic effect, we use the approximation gamma equal to first two terms because we deal with the weakly relativistic effect. Using the stretching variable, the stretching of independent variable and dependent variable and gamma in the first fluid equation, we then obtain the linear dispersion relation as a function of frequency and wave number. The group velocity obtained in this form. Then the third order harmonic with L equal 1 gives this Schrodinger equation in density of particle using phi 1 n11 equal to k square plus alpha 1 phi 1 1. We take the final form of Schrodinger equation in this form. Now, for a small wave number, k goes to 0. Equation 7 reduced to this equation. This equation called the Schrodinger equation for small wave for a small wave number. Why we deal with this equation? Because we need proof that equation not valid in all wave number. That's this equation we prove that equal or similar to equation obtained by KDV equation, Schrodinger equation obtained from KDV equation for a small wave number. Now we employing the reductive perturbation theory to obtain the KDV equation. Stretching in this form, and we take dependent variable as expanded as using the previous equations in the system of fluid equation, we obtain the KDV equation in the form. Then, now we derive the derivation of nonlinear Schrodinger equation from KDV equation, small wave number approximation. The KDV equation is written as in this form, and we expand in bar in this form, and we use this stretching to obtain the linear dispersion relation and the compatibility condition. And then finally we obtain the small wave number Schrodinger equation, which is similar to Schrodinger equation obtained from a finite Schrodinger equation at the limit k goes to 0. Log wave solution. The first log wave solution for equation 8 is the four. It takes the four results and discussion. First, we studied the variation of angular momentum with wave number with the for different value for u0 divided by c. If we increase u0 divided by c, we know that the angular frequency decrease with increasing this ratio. But for increasing the temperature ratio, we know that the angular frequency increase with increasing this ratio. That is ratio Ti to T electron. The variation of the group velocity with non-extensively parameter. Now, we studied the variation of group velocity. This group velocity, we know that the variation, the increase of u0 to divided by c, not effect on the group velocity, but increasing the non-extensively parameter increase the group velocity. On the other hand, increasing the temperature ratio and increase Q, increasing the group velocity. Now, to determine the stability and the instability of the system, we deal with contour plot of the product BQ equal 0. Now, we have a contour plot product of the product PQ equal 0 depicted against T wave number and Q non-extensive parameter. We know that the increasing of non-extensive parameter increase the critical wave number. The region of BQ is larger than 0, this unstable region, and the region of BQ less than 0 is the stable region. We find that The stability decrease with increasing sigma parameter or temperature ratio. Now we contour plot key sigma plane. We note that increasing the Q non-extensively parameter increase the region of stable and reduce this region of unstable but increase the critical wave number. Finally, contour plot. Then contour plot with key use zero
I think Nora have lost connection and she is back again. Nora? Yes. Nora Al-Shafi is back. Thank you. She will start presenting again.
Hello?
Yes, you are audible and visible as well. Can you?
Sorry, sir. There is
Yes.
a problem. Now to study the 3D plot of ion acoustic rock wave amplitude for different U0 divided by C, we note that the increase of this ratio E at U0 at 0.1, the amplitude is less than obtained by U0 divided by C equals 0.15. Now to study the 2D plot of ion acoustic rock waves amplitude for different value of U0 divided by C, and where for Q less than 1 and Q larger than 1. For Q less than 1, we show that the variation of in the amplitude and width is very small. And for Q أكبر من for Q larger than 1, the amplitude increase, very increase. Also, we have plot for different Q. For Q less than 1 and Q larger than 1. We find that amplitude very 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 variation with Q uh, larger than 1, and for Q less than 1, small variation. Finally, unlike effect with sigma, we show that for Q less than 1, the increasing temperature ratio decrease the amplitude and width, which increase the stability of the system. But for Q is larger than 1, increasing sigma increase the amplitude and the width of the log waves and increase the energy of the system. Appendix. This parameter used in previous equation. Constant. Conclusion. We In conclusion, we summary some important points. First, we obtained the nonlinear Schrodinger equation for large wave number, and secondly, we take the small wave number approximation. Key goes to 0, and within using the reductive perturbation, we and obtain the KDB equation, and from this KDB equation obtain the nonlinear Schrodinger equation for a small wave number, and study the stability and instability of the system and the effect of physical parameter in regions and log wave solution. Finally, thank you for your attention. Hello.
Yes, thank you, Nora, for your talk. And we have a question from Tuhil Devnath. So he is asking why frequency decreases with increasing value of U0 by C.
As the particle velocity increase,
Yes.
this
Frequency, why
increasing
frequency decreases with
making
increasing value of beta.
source here.
Yes, I say that why frequency decreases with increasing value of U0 by C.
Sir,
Why does frequency decrease with increasing value of U0 by C? I think
hello.
yes, hello. Okay, Nora, you can just answer in the YouTube chat box because I think the network is failing. So thank you once again. So your group and your friends, Mahmoud Bakri and the other participants, thanks to all of them for making it a international platform. So thank you once again, Nora. So right now we'll be having our next invited speaker, Dr. Amar Prasad Misra. So from the Visvabharati Shantiniketan Mathematics Department. So Amar Prasad Misra is often referred in the literature as A.P. Misra, whom you have already, my students and participants, they have, most of the time they have referred to A.P. Misra and A. Roy Chaudhary and Chandan Bhaumik, and P.K. Shukla. These are the common names that they often read about. Thank you, sir, for being with us this evening. And the title of the talk that Dr. Mishra is going to present today is Generation of Wakefields and Electromagnetic Solitons in Degenerate Plasma. So this talk will be very much interesting as there are some recent advancements in the Wakefield, and often in the literature this is a very hot topic. So I would ask the students and the participants to pay your attention and store your questions, because after the talk you can have our renowned AP Mishra to sort your queries. Thank you. Thank you, sir. Please.
So thank you, Swarniv, for your nice introduction, and also for inviting me to this nice platform to present and share my research work. So just let me share some screen. So is it okay, Swarniv?
Yes, it is absolutely visible and audible.
I can start. And is it audible to you? Otherwise, I will use my headphone.
No, it is audible. And just I think your video is turned off.
Yeah, should I on it? Keep
Yeah,
on.
before you turn it on, then it would be okay.
Okay, let's see.
Yes. Yes, sir, it is visible.
So, okay. So
Fine.
I would like to present, I was wondering what will be the topic for this platform. Anyway, this is the generation of Wakefields and electromagnetic solitons, especially in high density plasmas, where the particles are said to be degenerate. So my intention is to give some basic knowledge on, first of all, how the Wakefield is generated, and also how the transition from Wakefield generation to soliton formation takes place, and also what are the conditions, especially in relativistic degenerate plasmas. So outline is, I will give some basic concept on wake excitation. So how it can be related to some natural phenomena, which we observe also in the open ocean whenever the boat travels through. And how the transition from Wakefield generation to the soliton formation takes place. Because one way is to, we can expect some kind of generation of Wakefields to accelerate the particles. And in other sense, the soliton formations can have the basis for, say, transmissions of information as a pulse. So, and also finally, I would like to investigate what is the condition for the stability of electromagnetic solitons, and how far the electromagnetic soliton is stable, and also whether there is any parameter reason that the electromagnetic solitons can be unstable. And also I will give some recent developments, theory as well as experiment, and finally I will conclude. So the basic thing is, why do we use a laser plasma accelerator? So naturally the question is, instead of the so-called conventional particle accelerators that you know are very large, in the sense it can have 100 meter to more than that, also long. And also the more important is that it is expensive. So the cost is the most important factor. And usually what happens, the conventional particle accelerators, they use the radio frequency waves to accelerate the electrons. And also they have some limitation in acceleration field, because it can produce only up to 100 megavolt per meter. And also it has a limitation due to the electrical breakdown of the material. So that naturally there may not be some continuous process to keep accelerating the electrons. So what is then the way? So we can use some lasers which can drive the plasma particles to high speed. In fact, it can produce the higher acceleration gradient of 1000 gigavolt per meter with intensity of 100 terawatt lasers. So this is, it's a challenging one, and also people are doing experiments for that. what will be what will be an alternative acceleration scheme instead of usually investing on the conventional particle accelerators. So the concept is, you see, when a boat travels through water, it produces a wave behind it, so which we observe, and what is called a wake. And in fact, the phase velocity of the wave is equal to the speed of the boat, because as the boat travels in the forward directions, so behind the wake is generated with the same phase velocity. So similar technique can be applied in case of electromagnetic waves or laser pulses whenever it passes through a plasma medium. So that means one can use a laser pulse that can travel at the speed of light in vacuum, and which can drive a plasma with a strong wave behind it. Now, usually what happens, the wave so generated is basically an electron plasma oscillations, which have some frequency, is the plasma frequency that we know. And because of the high frequency oscillations, and also because of the high inertia of the ions, so they can only form the background plasma. So naturally we have a strong, very strong electric field. So that will be clear from the next slide. So what happens? You see, the most important part is the quantum force, because the wake that is generated behind the laser pulse is driven by the quantum force. And the quantum force is basically a particle, especially electron, experiences in a fluctuating electric field whenever, because this force has the tendency to push electrons away towards the weaker electric field. And in fact, it doesn't depend on the charge of the particle. So then in fact, whenever the particle oscillates at its position at some point, about some point, so the driving force, the quantum force, will have the tendency to drive away towards the weaker electric field. And in fact, if we apply it in an electron and plasma, so because of the heavy inertia, so you see, this is an example. So if we have a laser pulse passes through a plasma medium consisting of electrons and ions, and because of the light nature of the electrons, the quantum force will push away the electrons on either side. So, and as soon as there is a gap, because ions cannot move because of the inertia, so that and there remains there is a creation of the ion cavity. And in fact, whenever electrons are away from the stronger region to the weaker electric field, so they can turn back once again, because when electrons are away from their positions, so there is a separation of the charged particles. So in fact, due to the separation of the charged particles, the electric field is created, and which then acts as a restoring force to bring back the electrons to their position, so that there is an electron flow. And in fact, ion cavity is also formed with a high electric field, and it has the direction, outward direction, so that whenever the ion cavity is formed, it can produce the strong electric field, and so that electron bands can move with high speed behind the laser pulse. So this is the basic scheme for the laser Wakefield acceleration. So now what will happen, and I will describe here the mathematical formalism. So how to describe the laser pulse, and how to describe the dynamics of the electrons. So as you know, the starting point is basically the Maxwell's equations, Ampere-Maxwell's equation. And also, we define the vector as the scalar potentials through this relation. Then we use the Coulomb's gauge condition to find the wave equation for the electromagnetic wave vector potential. And gamma is here the Lorentz factor. So next, to describe the dynamics of the relativistic electrons. So what happens is that you can have the particles with a high speed so that it can move with the speed of light in vacuum. Or we can assume that the particles have the relativistic speed. In fact, as well as also they are degenerate in the high density regime. In fact, in astrophysical plasma, the particles are highly dense, so closed, there is no lower energy states. So we can assume those particles are the degenerate particles. And also degeneracy pressure. So how do they keep along with the electromagnetic fields the particle in equilibrium? So this is the equation of motion whenever the particle have electrons have relativistic degeneration. So gamma is here the relativistic factor, and also this is unusual whenever there is a pressure gradient term, as well as the time derivative part of the pressure. So we have to be careful in writing down the relativistic dynamics of electrons, especially whenever there is a pressure, maybe degeneracy pressure or the thermodynamic pressure. And the usual continuity equation and the Poisson equation. Here H is the enthalpy, which is the sum of the pressure as well as the internal energy density. So whenever if you just simply have, if pressure is 0, so you can discard this term and you can have the usual relativistic dynamics of electrons. So now, because of the simplicity, we consider in a propagation in a single directions, for example, z direction, and all the dynamical variables are necessarily functions of z and t. We have some transverse electromagnetic fields as well as the vector potential and the velocity, and some of the velocities that is produced due to the Lorentz force. So there are some intermediate calculations. And what important is that here the longitudinal electric field is driven by this electrostatic potential. We can write as a gradient of something, as you know. So then, and also these equations to be coupled with the electromagnetic wave equations together with the density fluctuations equation. So that we will see in the next slide. So now some calculations to derive the, say, velocity expression, Weber velocity, as well as how the gamma factor, the Lorentz factor is modified due to the enthalpy and also the pressure gradient force. And ultimately, if we just equate the transverse component of the electromagnetic wave equation, so then you can have this equation 9. So we have this time evolution part, the dispersive term, as well as the nonlinear part. So nonlinear term involves still the velocity, transverse velocity. So we have. So then after elimination and taking out some components, power components from the equation of motion, we can have in the intermediate calculation the quantum force expressions, which I have described before. So ultimately, we can have some coupled equations. So before that, we have some usual Chandrasekhar pressure equation, the degeneracy pressure equation that you know. This is the pressure, this is the internal energy, and this is the degeneracy factor, which is the Barney momentum divided by the momentum. And of course, the enthalpy is is expressed in terms of the degeneracy pressure. So naturally, for a given density and also in the fixed mass and also the constant velocity c, so as the R varies, maybe less than 1 or greater than 1 or of the order of 1, as one goes from say weak relativistic to moderate relativistic degeneracy and to ultra relativistic degeneracy regime, so then one can consider different parameter regimes for the different plasma densities, and we will see how the degeneracy factors involves and behaves in the case of the generation of wake fields as well as transition from Wakefield to the soliton formation. So now the first aim is to express the equations in a reducible form, in a convenient form, whenever we consider the wave amplitude of the order of say unity, not so high and also not so small. And so these equations, one for the density fluctuations, especially the electron plasma oscillations that are driven by the conformative force. This is the nonlinear force. And also this is the electromagnetic wave equation that are coupled with the electron density fluctuation. So this equation shows that the electrons have, due to the conformative force, can have oscillations. And the parameters involved are basically the degeneracy parameter is very much important, and how, as you will see, how it contributes to the dispersive term through the delta, because delta is a function of eta E, and eta E also involves R0, and R0 is the degeneracy parameter. So naturally, you can classify the parameter regimes with it's a small value or it's a large value or smaller values or larger values. So that will be clear also as we go on the next slide. So now, because we would like to investigate the dynamics numerically, so one can investigate numerically solving equations 12 and 13. And because here we are looking for the structure, so one can use the Lorentz transformation. So we can co-moving frame by assuming J equal to Z minus, actually this is the group, this in fact the M may be the group velocity, actually M is the group velocity because we are considering the electromagnetic wave. And if we assume the electromagnetic wave amplitude of the form which has some time phase as the amplitude is a function of J, so then equations 12 and 13 are reducible in the more convenient 14 and 15. But one has to keep in mind that there are so responsible terms which can act on the dispersive term. The dispersive term is basically due to the separation of the charged particle, as you see in the Poisson equation, and also through the pressure gradient force due to the relativistic degeneracy pressure. So that means the degeneracy pressure has the key role in controlling the dispersive term, and hence, whenever there is a more dispersive than the nonlinearity, so you can expect some kind of soliton formation. So that means you can have from a non-dispersive to dispersive transition, as well as dispersive to non-dispersive transition. So that whenever the dispersive to non-dispersive transition occurs, we can have some kind of Wakefield generation and the vice versa. So now, before going to the nonlinear analysis, we can predict. So what is the region for the existence of electromagnetic solitons? If we assume simply the wave amplitudes of the electron density fluctuations as well as the electromagnetic wave are small, so then you can reduce equations, the previous equations to 16 and 17, and a simple solution of the form exponential factor gives us some kind of region of the existence of the soliton, which involves the soliton speed should have some minimum and some maximum values. So it has the upper limit 1, and also the lower limit is a function of the electromagnetic wave frequency. So now from the basic ideas, if we simply consider a Gaussian pulse, for example, A square is exponential minus I square by LP square, where LP is the pulse size. So then naturally, how much pulse size is required to drive the electrons? So you can simply calculate. And also, whenever the laser passes through the plasma medium, so it can resonate the particles. So then what is then the pulse size should be, so you can find it from here. And in terms of course, the units of the plasma period, because electrons oscillate with the plasma frequency. So naturally, next is for generation of the Wakefields. So you can specify the pulse size. It must be smaller than the scheme depth, the C by omega p. But we will see non-relativistic dynamics. The group velocity you will find simply the C square root of 1 minus omega p square by omega square. You can derive from the basic equations. However, in relativistic motion, so we can replace the density by n0 by omega, when n0 is basically in the laboratory frame density. So you see how the group velocity is modified. So now you can calculate the field strength, how much electric field is required. So approximately, for example, if you have a high density regime, 10 to the power 28 per meter cube, and if you have an amplitude of the electromagnetic wave of the order of 0.5, and so that you can have the accelerating electric field strength, which is 2000 gigavolt per meter. So in this way, you can predict and also calculate the electromagnetic field strength for a given pulse size and also in a given medium of plasma density. So these are basically the simulation results from the literature. So they have considered simply without any pressure gradient thermodynamic force, some relativistic dynamics of electrons, and by means of the laser pulse, how the laser drives. They have calculated the group velocity, and which basically coincides with the simulation code, PIC simulation code. And in fact, the group velocity decreases, initially have some constant as the density increases. So that one can have, and one can also calculate the critical density beyond which the Wakefield generation may cease to exist. Because the electron, once you increase the density, you can have the more dispersion than the nonlinearity, and also in the low density region, whether the Wakefield generation is favorable, that will be clear also. So now we have to keep in mind that we can apply the laser pulse as an accelerator for the acceleration of the electrons. Electrons will be energized to move with the speed of light in vacuum, and the Wakefield is generated behind the laser pulse. However, the thing is that, so if the electrons travel slightly faster than the wave, what will happen? So then electrons will, I think, lose energy, because electrons will give energy to the wave. So eventually get decelerated. So this is called the dephasing. So dephasing can also occur in the case of laser-driven accelerator scheme. So then what will be the idea to control the dephasing? So we have to, so the electrons can follow the wave. So the more wave can be generated. And also we can calculate the time. So how? Because we have a relativistic electron, say, with a speed v approximately speed of light, and gamma is approximately 1. So then the group velocity which we have calculated before, and simply we can, because if the electrons can move to half a plasma wave out of the phase, so then we can have the time from accelerating to decelerating field. So then you can calculate the time. And the option is that, so we can create the plasma wave, so which will gain the energy. And this must come from the driving pulse, of course. And that energy which we can calculate into the electric field is 1/4 of the electric field amplitude square, the transverse electric field. So in this way, we can calculate the time period of oscillations, so that electrons can follow the wave, and also it cannot be dephased, so that no more deceleration can take place. So now those are basically the graphical plots and also the numerical simulation results of the two wave equations. And in fact, you see, this is clearly the oscillations behind the laser pulse. So, and in fact, whenever there is a amplitude, low amplitude, if you consider laser pulse with amplitude 0.01, and if we specify the degeneracy parameter, so which signifies the low density regime, so then you can expect the Wakefield generation. And this agrees with the classical results that I have shown before here also, these results. So the physics is that whenever the degeneracy parameter is increased, so you mean the as you enter from the low density to high density regime, so then dispersive effect becomes dominant over the nonlinear effect. So that is why you cannot expect the Wakefield generation in the second case. So now, what will be the fixed values of the electromagnetic wave frequency and the group velocity? So you can expect here the laser pulse size should be 0.1, and the group velocity of the order of the velocity of light, and this is the electromagnetic wave frequency. So this is most important, and of course the density regime which we consider. And in fact, the Wakefield generation is also is being suppressed whenever you increase the density through the degeneracy parameter. So now we can have the transition. So how the transition takes place from the Wakefield generation to soliton formation. So naturally, one is that you can increase the initial pulse amplitude. So by keeping the group velocity of the order of 0.1 is if you just reduce that. So because if you just go back to the equations, the dynamical equations here, so the M is responsible and delta through the degeneracy parameter is responsible, which controls how much dispersive effects dominates over the nonlinear terms. So that is why M and delta, which plays vital role, there is the group velocity relative to the speed of light in vacuum, and the delta E, which is as a function of the degeneracy parameter, so that high density regime, low density regime, and of course the pulse size of the laser, the amplitude, I mean the amplitude, also responsible for the generation of Wakefields and electromagnetic solitons and their transitions. So here, as you increase as you go from low density to high density regime with the R equal to 0.2, so you can expect the localization of the electron plasma oscillations. So that means you can expect some kind of transition can take place from the Wakefield generation to the solid information. So here, this is some typical examples of the electromagnetic soliton. If we find some analytic solutions, and for different values of the wave amplitude, the frequency and the group velocity ratio, and of course the laser pulse size. So you can expect different nonlinear structures. So the next part is, so far we have discussed the generation of Wakefields and electromagnetic solitons and their transitions. So we have considered an electron ion plasma, especially the relativistic degenerate electrons and ions in the background. And we have considered some kind of electromagnetic waves to interact with the electrons non-linearly. The main force is the undermotive force, the driving force, which can drive the electrons and which pushes the electrons away from the stronger to the weaker region, for which there is a electron ion cavity can be formed with high electric fields. So due to the separation of the charged particles, electron can go back to their initial positions, and because of the high fields created by the ion cavity, electrons get accelerated and they can move with a high speed close to the speed of light in vacuum and behind the laser pulse. So next part is, so if the electromagnetic soliton is formed, so what is the stability? So how long they will be stable? So whether we can investigate their spatiotemporal evolution, as well as what are the criteria for which we can predict at least some parameter values, what are the restrictions for the degeneracy parameter for the stability of electromagnetic solitons. So we have recast the basic equations which we have numerically solved. So now our idea is how long the soliton is stable and what is the condition for that. So simply our aim is, because we are considering the envelope waves, electromagnetic waves especially, so then the basic idea is to convert in 1920 to a NLS equation, nonlinear Schrödinger equation. So for that, because we have considered the linearly polarized electromagnetic wave, so we can have odd as well as even harmonics for the electromagnetic wave field and for the electron density fluctuations. So simply, if we just substitute 21 into 19 and 20, so then you can have the simple, not a simple one, but you can have some local as well as non-local terms. So local term is basically the Kerr nonlinearity, the cubic nonlinearity, and you can have, of course, the derivative nonlinear terms, which we call as the non-local terms. So basically, our aim is to see how the non-local terms, because usually we have, due to the cubic nonlinearity, we can have some coherent structure like envelope, electromagnetic wave envelope. But here, how the non-local terms be responsible for the stability of electromagnetic soliton and also their instability. So then you look for a solution in the form with an amplitude and phase, and by considering, by expressing this one into a moving frame of reference. So this is an implicit form of the, as the typical form of the electromagnetic soliton. Yes. So next part is, we can use VK Hakitov-Kolokov stability criteria. So as per the criteria, we calculate the photon number, which is actually the totality of the electromagnetic wave amplitude, square of the electromagnetic wave amplitude. And in fact, if dV0 d lambda square, here lambda is gone through this one, which involves in the phase, and also it behaves as an Eisen frequency because it's directly appears as a coefficient of time part. And in fact, if this derivative is greater than 0, we can say the soliton is stable, otherwise it is unstable. But this is not so simple. First of all, we calculate the photon number. What is the photon number for the given electromagnetic soliton? And in fact, there should be some critical eigenfrequency, critical lambda. There will be some kind of instability threshold, and also stable region and unstable region, and at which we can see also P0 reaches a local maximum value. Let's see. So if you just plot P0 simply with respect to lambda, so you can have different curves for different values of the degeneracy parameter as well as the velocity of the soliton in the moving frame. So in fact, as we increase, this is the solid line for initially for R0 0.02 and V0, the standing soliton. Now you start increasing the velocity of the electromagnetic soliton. So then what happens? This red solid dashed line, basically the threshold value shifts. And in fact, because this is a curve, so you can have the slope dp lambda square, which will be greater than 0 on the left side. So then ultimately we can consider the regions and the threshold values, which varies as you increase or decrease the degeneracy parameter as well as the velocity of the solitons. And in fact, these are basically the critical values, the threshold values. So different limits, in order to satisfy the stability condition, we have some limits for lambda as well as V0. So if we just contour plot in the lambda V0 plane, the curves which are responsible for the stability of electromagnetic solitons. So what happens? We have considered three different regimes. For R0 equal to 0.02, if we can see, call it as a weak relativistic degeneracy, and this is the B plot is for the moderate value of the degeneracy parameter, and higher value, that means strong degeneracy of rank. So in fact, if we classify the stable soliton region and unstable soliton region, so naturally as R0 increases, so that means as one moves from low density regime to ultra relativistic regime, high density regime I mean, so then the stability regions get reduced significantly. So naturally a question arises, so if you just have a value, for example, say R0 equal to 100, so what will happen? So there will be no picture, no stability region. The answer is that, so this is the limitation of the Kolmogorov stability criteria, that which we have predicted here, that so in order to be in order to see the stability of electromagnetic soliton in a strongly or ultra relativistic degeneracy, so the criteria we can have to help of some kind of other stability criteria through the Hamiltonian or some other analysis. So that for R0 much greater than 1, so we cannot have a region of stability. So that doesn't mean that the electromagnetic waves are unstable in a high density region. So this may be the limitation of the stability criteria. So that once we must be careful about how to use the stability criteria, to what extent the results can be valid. So these are basically the restrictions for the degeneracy parameters and also for the stability criteria. So now, if we just to predict from here the analytic expressions and from the stability criteria, the regions of stability and instability, and if we apply those values here to the numerical simulations, we have almost a good agreement that analytical results will agree with the numerical simulation results. So because this results is basically whenever we have a weak relativistic degeneracy regime, so that soliton the electrons oscillates, the electromagnetic pulse oscillates for a long time. And if you increase the velocity, so the figure is basically the standing soliton, and you see it is always stable because it evolves with a steady state and with a oscillation for a long time. And for the CD plot, if we just increase the velocity, V0 equal to 0.2, so the moving soliton actually travels. However, as you see, the amplitude decays, and ultimately, as time goes on, it also oscillates with the steady state oscillations. So that means still, though the electromagnetic wave amplitudes get reduced, but it evolves steadily. So the oscillation, electromagnetic oscillation is stable. Now what happens for the next case, if you, in the EF plot, if we simply increase the wave amplitude, so that not only the wave amplitude increases, so this is the symptom, this is the onset of the collapse. Basically, the soliton is no longer stable, and in fact, what happens, there may be some wave singularity that may be created. Of course, the wave singularity is not a physical one, which may be removed due to some other physical which can intervene to remove the singularity. So what is happening here, the wave amplitude grows as the time goes on, and eventually, ultimately, for a long time, after a long time, the soliton collapses. So this is the scenario. So how long the soliton is stable, and for a standing soliton as well as for a moving soliton. We have considered, let's see, sorry, these are the three pictures, three graphs to see that the solitons, how the evolves and it get collapsed with an increase of the degeneracy parameter from 0.02 to 0.08 and to 2, which is greater than 1, strong degeneracy. So now we can summarize the results, and what happens, we have some kind of parameters, the degeneracy parameter as well as the group velocity, electromagnetic wave envelope, and those are basically responsible for the formation of Wakefield generation as well as the soliton formation. Of course, there is some critical value for the transition from Wakefield generation to the soliton formation. And whenever we do a simulation study, we have seen that there must be some typical pulse size which must be less than the skin depth, C by omega P. And of course, lower amplitude favors the Wakefield generation, and higher amplitude with higher amplitude of the electromagnetic wave favors the generation of electromagnetic soliton. And also the dispersion, there is a critical density, I mean there is a critical value of the degeneracy parameter. So high degeneracy parameter gives the formation of electromagnetic soliton, because in the high density region, naturally the dispersivity effect dominates over the nonlinear effects. Okay. So next, we have studied the electromagnetic solidity. So which we have seen that for an isolated soliton with a constant photon number, an increase of the soliton velocity results into a reduction of the maximum amplitude, broadening of the soliton profile. So the solitons can move for a longer time depending on the degeneracy parameter as well as the soliton velocity. And we have studied the stability of the solitons, basically deriving the generalized nonlinear Schrodinger equation. So these are the recent developments for the generation of Wakefields and electromagnetic solitons. I can quickly move because those are available in the literature. So one thing is that there is an advanced proton-driven plasma Wakefield acceleration scheme. That is a project at CERN. And of course, it is a proof of principle experiment investigating the use of plasma Wakefields driven by a proton binds to accelerate charged particles. So now we can conclude. Mostly I have described before in the previous slides, so that once we just recapitulate, we must have the amplitude of the electromagnetic wave that should have some ranges, some smaller and larger. Also, we can have the density regimes for different values of the degeneracy parameter, and of course the velocity in the moving frame. So Wakefield generation is naturally suppressed, and formation of electromagnetic soliton is to be expected for a high density regime. Of course, some other conditions have to be fulfilled. In fact, in some other moderate regime, density regime, and also strong density regime, the Wakefield generation and electromagnetic solitons can also be formed. And we also, from the stability of the electromagnetic solitons, we can see the stability of electromagnetic soliton is very much useful for the formation, for the relativistic dynamics of solitons behind the laser pulse inside photon condensate. In fact, a more detailed analysis is required to have some detailed parameter regimes. So, as expected, results will be useful for understanding the interaction of electromagnetic waves with electron density fluctuations and for the next generation high laser fields, and also for the particles that are emanating from the astrophysical objects. So these are basically, as you know, the very well-known paper by Tajima and Dobson for the laser Wakefield acceleration scheme, and we have some other papers. And they are my collaborators, Devjani and Seema. So also there is a funding from UGC and also ACRB scheme. So thank you for your kind attention.
Thank you, Dr. Mishra, for your wonderful and enchanting talk. So,
any question?
Any questions? We are waiting because it will be a 20 minutes difference, 20 seconds difference between the record and the live. Just waiting.
Okay.
Well, there is one student from Visvabharati, Yash Novi. Is from Visvabharati.
Are they?
Yash Novi from
Okay.
Visvabharati. Is live here.
So can I wait for some queries or questions, Swarniv?
Yes, just.
Sure.
So I have one question.
Sure.
These days there is an increase in the study of MHD models.
Yes. MHD waves, you mean?
MHD waves. So
yes.
MHD waves, is it from the simulation viewpoint or from the practicality it is more effective? Actually, there are groups of people who are critical about this discussion. So I want to just have a
yes, MHD waves are, you mean whether there is some simulation studies going on for MHD waves, or some analytical studies, or some for the propagation of basic MHD waves?
No,
in fact, MHD waves, to study the MHD wave, there are some group also for they are considering some simulation studies, and of course we can study some basic waves, for example Alban waves, magnetosonic waves in different plasma regions. So those are basically the MHD waves that can propagate in the plasma in different plasma media. So one has to consider some MHD equations, wave equations, starting from Maxwell's, and of course some relativistic dynamics, etc., etc.
Yes, I also think that because while confining a plasma, magnetic field is most of the time used, so MHD model would be a better uh, model to study because magnetic field effects are always present.
Yeah. So MHD waves, yes. For example, albanic soliton, magnetosonic soliton, albanic shocks, magnetosonic shock-like waves. So those waves can be also generated uh, for the yes, for MHD waves. Those who are interested. The simulation study is another way to consider starting from the basic MHD wave equations.
Well, one question, Cerberus, I think it's an outstation question. That means from abroad. So it is, the question is, how can we manage the convective derivative from the basic equations except numerically? How can we manage the convective derivative from the basic equations except numerically?
You mean for what purpose?
Well, I'm not clear with the question. I think regarding the simulations, question is, how can we manage the convective derivative from the basic equations? Let me ask for a clarification.
So in case of MHD waves or non-MHD waves?
I think in regarding with the MHD waves there.
Yeah, yes, MHD waves, that is the most important question also. In fact, for atmospheric gravity waves, we use the MHD wave, especially for compressible fluids, incompressible fluids. In fact, whenever we consider the time, actually the convective derivative comes in the fluid dynamics, because there is a time derivative part as well as some the convective part. So basically except the numerically you have to consider the time derivative as a whole, and depending on the approximation you cannot ignore just what kind of waves you are considering. It depends whether compressible fluid or incompressible fluid. It's very difficult to give one answer to this question, because you cannot ignore. If you consider the convective derivative, you cannot ignore also.
Well, that's the nonlinear.
It depends on the what kind of waves you are considering. It's a compressible fluid or incompressible fluid.
Yeah.
That is important also, because you cannot by hand ignore. Because I have considered some problems for atmospheric waves in which the convective derivative, I cannot remember right now. Maybe if someone can ask me, I can give more clearly the answer whenever I go through that problem also. Because it depends on the problem we consider. Whenever the ddt is simply the time derivative as a whole, not the partial derivative plus the convective one part, as in the fluid dynamics.
Well, I think they have clearly understood that where the importance of these waves and the wave mode, the different aspects of the study that is important.
Yes.
And let me thank you once again for being with us, because here most of the audience are almost graduating final year students and MSc students, and few are the research scholars. So for them, your talk was very much
Yeah. This talk is especially for the research scholars maybe. So, wait, okay, so this is the direction how the research is going on recently, and that is just an idea. So how we, the mathematician and physicists, can work on these areas, so the graduate and postgraduate students can be motivated for that. So I could have started from some basic other things, also basic plasmids, etc. I think they are very much known in the literature and also MSc courses and BSc courses.
Well, thank you, our audience, and for your participation, and of course, Dr. Mishra, for your time and involvement with us. And from my side, I would like to thank again. And next time when we come, and we'll have some more advanced topics, because this workshop which we carried out for 2 months, it was a basic, though some of the works were quite good. And next time when we come, we'll have uh, senior professors and scientists, so they will be also with involved with the program. And we hope that sir, you would be also with us like you have always been. Thank you once again.
So thank you all the participants, and especially to Swarniv for such an initiative during this pandemic situation also. That's a nice idea,
Thank you.
is
Thank
to
you.
meet together so in the online platform. So thank you. Okay.
So dear students and audience, so tomorrow will be here at the same time and same place, and kindly follow the updates in the website and YouTube channel. So as of now, uh, it's almost done for this day. And regarding tomorrow's program schedule, we have 2 invited talks by Professor Narishpal Singh Saini from Guru Nanak Dev University. And it is scheduled from 6 to 7. The title of his talk is The Theoretical Study of Nonlinear Structures in Space Dusty Plasmas. So again, we get a flavor of the astrophysical plasma. And next, we have Dr. Sukhdeep Kaur from Guru Nanak Dev University. And the title of his talk is Propagation of Characteristic of Laser Beam of Different Intensity Profile in Plasma and Simulation of Terahertz Waves in a Parallel Plate Waveguide. Well, terahertz generation and its investigation is one of the additional and most interesting part of plasma physics study. So all and these talks will be on different aspects, and we have our student presenters as well. And on the final day, that is 11th, and day after tomorrow, we'll be having one guest lecture by Dr. Mukesh Ranjan from Institute of Plasma Research, Gandhinagar, on the industrial applications of plasma. But the time is from 5 p.m. So on the closing day, we'll just graduate with our students and participants. So as of this day, this evening, thank you. Thank you very much for your patience. Good night.